Today is trigonometry lesson number 2. And what we're going to do today is give names to the mathematical names to those ratios in right triangles that we were talking about. And we're also going to talk about some different names for angles using Greek letters. And then we're going to practice on some triangles that are a little bit more complicated than what we've looked at before, just because they have some irrational lengths in them. So we've been studying right triangle trigonometry, and we've been looking at the ratios for the different side lengths. So I'm going to label this triangle. We're going to call it triangle maybe X, Y, and Z. Okay. And so using our notation that we talked about earlier, the side that's opposite angle X, I'm going to call little x. The side that's opposite Y, I'm going to call little y. And the side that's opposite Z, I'm going to call little z. And I'm just noticing here that that one of the reasons you don't see this particular letter choice maybe a lot of times is that small x looks like big X, and small z looks like big Z, and small y kind of looks like big Y. So maybe this wasn't a good idea. How about if we change it and we're going to use EFG, because those will look different. So that's what I'm going to do. So let's change our triangle. We're not going to call it that because it it can be ambiguous sometimes. The meaning is hard to remember. So let's call this E and this F, capital letters for the vertices, and then the little e, that's clear, the little g, that's clear, and the little f, that's clear. It's a little better, I think. All right, and so we were looking at some specific ratios. One ratio that was important was the ratio that was opposite over hypotenuse. Okay, so for example, if I was looking at angle E right here, the opposite over hypotenuse would be, if I'm looking at angle E, it's always relative to the angle that you're looking at. So opposite over hypotenuse would be little e divided by the hypotenuse, which is F. And so that would be that ratio. Now, on the other hand, if I was looking at opposite over hypotenuse and I was looking at G, so here's G down here. So it's going to be different. So the opposite over hypotenuse would be small g over F. So we can have the same ratio, opposite over hypotenuse, but depending on which acute angle that I'm talking about, it's going to give you different answers. So to get around that, we give these ratios names, okay? And so the name for the opposite over hypotenuse ratio is sine. Now it's sine, S-I-N-E, but if you look on your calculator and and when we write it as S-I-N. And so if I was going to talk about this over here, instead of just writing, saying I'm doing opposite over hypotenuse for angle E, what I would write shorthand for math is I would write the sine of E. So I'd write sine, but I don't write the E because we abbreviate it. So I'd write S-I-N with a capital E. And that E is not part of the name sine. It's for angle E. The part of the sine that we write is S-I-N. Now for the blue angle, the angle G, what would we write for that? Well, we're going to write S-I-N for sine, and then we're going to write G. So it looks like sing, kind of. So this means the sine of angle G. This means the sine of angle E. Now make sure you write this an example in your notebook, because you're going to have to refer back to this. So here I have another right triangle, and let's call this PQR, and here's my right angle. And so the other ratio that we thought was really important, so small p, small r, small q. Okay, so the other ratio that was special was the adjacent over hypotenuse. So let's write that in green. So adjacent over hypotenuse. And this has a name as well, because again, it's related to, you have to specify which angle you're talking about. And so just like we talked about for the sine, this ratio, which is opposite over hypotenuse, this ratio has a name, and this ratio is called the cosine. Because they're related, right? Remember what we saw was that if I have the adjacent over hypotenuse for P, that's going to be the same as the opposite over hypotenuse for Q, and vice versa. And so, cosine. So it's related to the sine, but it's not the same. It's the adjacent. And you're going to have to memorize this eventually, but for right now, make sure you're drawing a picture and putting some examples. So again, it depends what angle we're talking about, and this also has an abbreviation. This is abbreviated COS. So if you look on your calculator, that's the key that would be. It would be the COS key. And the cosine of these angles, so if we take the cosine of angle P, we're going to have the adjacent over hypotenuse. So this would be the adjacent to P would be Q, and the hypotenuse is R. So this would be Q over R. And if I did cosine of angle Q, so here's angle Q, the adjacent side is P, the hypotenuse is R. So this would be P over R. So here is another right triangle. Let's see, what letters should we use for this? How about N, M, and O? So this would be little o, little m, and little n. And so there's a third ratio, which we have not talked about at all. But if you remember back to the problem sets that we did, sometimes we did not know what the hypotenuse was. And so we had to solve a couple of problems to get to the answer we wanted. And so another ratio is really useful, is where we can avoid the hypotenuse altogether. And in that case, we're just talking about the two legs of the right triangle instead of the hypotenuse. And this ratio is called the opposite over adjacent, and we haven't had any practice with that at all. So this is the opposite over the adjacent side. This ratio only deals with the legs, and it's given the name tangent. And the opposite over the adjacent ratio for tangent is abbreviated TAN. And again, it's related to the angle you're looking at. So for example, if I look at angle M, the tangent of M is going to be equal to the opposite side, which is little m, over the adjacent side. So it's the side that's not the hypotenuse. So it's going to be side O. So this would be m over O. Looks like we're dividing by 0, but remember that's a O, not a 0. Then the other one, if we did tangent of angle O, you'll see that it's kind of interesting that it's actually going to be, because it's just the two legs, so it's the same two legs we had here, but they go in the opposite order. So it'll be O over M. So the opposite side of O is little o, and the adjacent side is M. So then this would be O over M. So you can see that these are reciprocals of each other. One thing you'll notice when we're doing these angles measurements, like sine and cosine and tangent, these three ratios that we were talking about, is they're only relative to the angles you're looking at. And so you notice that when we were using these letters, like when I used angle E, for example, it looked like it was part of the word sine, which is not so good, right? Of course, you would know from the context that it wouldn't be. So one of the reasons that, well, I'm assuming one of the reasons that mathematicians and scientists use strange letters, different symbols for things like angles, is to just avoid that. And so one of the common techniques to name angles is to, instead of just using the letters like capital A, capital B, capital C, and name them like that, is to give them a name that's special. Like one letter is called theta, okay? And theta looks like a zero with a little loop through it. It's a Greek letter, and its name is theta, theta. There are a couple more. There's actually lots of them, but these are the most common. Theta is often used for angles. Another one is an A kind of letter, but it's written as kind of a loop like this. It looks like a fish, I think, and it's called alpha. It's the Greek letter for A. Then the other one that is commonly used is a B, but it's made a funny B like this. It kind of looks like a broken heart. It's got that line going up, and this is beta. Okay, and so these are the three most common letters used for angles. And so if this is angle theta, I could refer to this angle. Well, one way I could refer to it is 90 minus theta, right? Because if this is a 90-degree angle, I know that this if I take 90 and subtract theta, that this would be this measurement. But another common way that I could name this is I could just say, well, I'm going to give it its own name, and maybe I would name this alpha. Okay. So that would be angle alpha. So then if I was talking about these measurements, I might do the sine of theta. I could do the tangent of alpha. Okay, or maybe I want cosine of theta as well. So that's a way to name letters using Greek letters. And there's lots more Greek letters, but these are the ones that we're going to use. So here we have a triangle, and just the common way that you'll see those measurements written, those right ratios that we want, is we'll have them for memory. We'll say sine of theta equals opposite over hypotenuse, and then cosine of theta equals adjacent over hypotenuse, and tangent of theta equals opposite over adjacent. So that might be like something that you would have in your notes to remind you. And what is theta? Theta is just some acute angle that you're interested in. It's never the 90-degree angle. It's always one of the other two. And so here's my triangle here. And let's give this triangle some values so we can calculate them. Let's say this side of the triangle is 1, and this side is 7. And so I need to find this other side. So I'm going to use the Pythagorean theorem to find this other length. And so we know that if I take the two legs and square them, 1 squared plus 7 squared, it's going to give me the hypotenuse squared, right? That's the Pythagorean theorem. So we have 49 plus 1. This would be 50 equals the hypotenuse squared. So the hypotenuse is going to be the square root of that. So the hypotenuse is going to be the square root of 50. Now, we're not going to leave it as the square root of 50 because remember we learned how to reduce these radicals like this, and we learned that this is the square root of 25 times 2. So this is really 5 times the square root of 2. So our hypotenuse length is 5 times the square root of 2. And so let's see if we can calculate these ratios that we're interested in. And so we might ask for what's the sine, and I guess we need an angle, don't we? So let's say theta is this angle right here. So it's the angle at the top right here. So I named it theta. And so let's see, sine of theta, that's the opposite over hypotenuse. So we go opposite, that's 7. The hypotenuse is 5 square root of 2. Okay. The cosine of theta equals the adjacent side, which is 1. So we'd have 1 over 5 square root of 2. And the last one is the tangent of theta. And tangent of theta is opposite over adjacent. So the opposite side is 7, the adjacent side is 1, so that would be 7 over 1. Now, remember, 7 over 1 is fine. That's 7, right? So that tangent is fine. But we have a problem here with the sine and the cosine. Can you see what the problem is? Hopefully you notice that it's got a radical in the bottom, which we don't like. So we're going to get rid of that. So we're going to simplify this by multiplying by the square root of 2 times the square root of 2, that giant 1. And so this is going to be 7 square root of 2. And then on the bottom, square root of 2 times square root of 2 is they combine to be square root of 4, which is 2. So I have 5 times 2 on the bottom. This would be 7 square root of 2 over 10. This one, we're going to multiply square root of 2, square root of 2. 1 times the square root of 2 is square root of 2. And again, on the bottom, we're going to have square root of 2 times square root of 2 is square root of 4, and that's 2. So 5 times 2, we'll have 10 on the bottom. And so this would be the correct answer. So the sine of theta is going to be 7 times the square root of 2 divided by 10. The cosine of theta is square root of 2 divided by 10. And the tangent of theta is 7. So I'm going to expect you'll get partial credit for doing 7 over 5 square root of 2, but I'm going to expect you to be able to simplify it now into the simplest radical form. So let's do a different example. So here I have this special triangle which has sides 1, 5, and the square root of 26. And so now I'm going to need my angles. So I'm going to put the angles in. And so those are my angles. So this particular triangle with these side lengths would have an acute angles. This angle down here would be 78.7 degrees, and this one would be 11.3 degrees. And so right now you wouldn't know how to do that, how to find those out, but you will eventually. So right now, here's my triangle, and I'm going to find those ratios that we were interested in. So let's say that let's start with the 11.3 degree angle, and let's find the sine. So the sine of 11.3 degrees, we'd write it like that, and our ratio is going to be opposite over hypotenuse. So that's the sine is the opposite over hypotenuse. So opposite is 1. The hypotenuse is square root of 26. So the sine of 11.3 degrees is 1 over the square root of 26. Now we don't want to leave it like that. So remember, we're going to multiply by square root of 26 with the square root of 26. And the answer we're going to write it as is square root of 26 over the square root of 26 times the square root of 26 is just going to give us 26. It'll give us a big number, but it'll be a perfect square, and it'll be 26. And so this would be our answer. 26 itself is 13 times 2. So both of those are prime numbers. So there's no factorization that we can do here, and no further simplification. Now let's do the cosine. So cosine of 11.3. And remember, cosine is the adjacent over hypotenuse. So if I look at this, here's my angle 11.3. The adjacent side is 5. The hypotenuse is square root of 26. So this is going to be 5 over the square root of 26. And again, to simplify that, we're going to multiply by the square root of 26, square root of 26. And we're going to have 5 times the square root of 26 in the numerator. And the bottom is going to be 26. And again, this does not simplify, so this would be the answer. The cosine of 11.3 would be that expression. Now, of course, we could actually divide this out and multiply by the square root of 26 and all that, but we're writing our answers in simplest radical form. All right, the last one we're going to do is the tangent. So if I look for the tangent of 11.3 degrees, that's opposite over adjacent. So the opposite side is 1. The adjacent side is 5. So this would be 1/5. Now we could do the same. We could go back and do the same thing for the other angle. But notice, remember, the sine of one angle is going to be the cosine of the other. So I already know that the sine of 11.3 is going to be the same as the cosine of 78.7, because we know that relationship, that the sine of this angle is going to be the same as the cosine of this one. And the same thing, the cosine of this angle is going to be the same as the sine of this angle. So I could write the sine of 78.7 is going to be this. And for the tangent, we also know that it's going to be the reciprocal. So the tangent of 78.7 degrees is just going to be 5 over 1, or 5. All right, so here is a triangle, and we're going to give it some side lengths and some angles. All right, so here is our triangle, and we can see that it has legs of length 1 and 2, and the hypotenuse is the square root of 5. We can also see the two angles. It might be a little hard to see right now, but this angle right here is 63.4 degrees. That's this one. And this other angle is 26.6 degrees. So it's kind of hard to see because of how small the number is inside there. So notice that if I add 26.6 plus 63.4, I get 90 degrees, which we would expect, because we know that the sum of the acute angles in a right triangle are 90. So what are you going to be asked to do with, for your homework assignment? Well, you're going to be asked to find things like, what is the sine of 63.4 degrees? What is the cosine of 63.4 degrees? What is the tangent of 63.4 degrees? And you're going to fill in a table with that. And then similarly, we're going to be doing the other angle. So the sine of 26.6 degrees, the cosine of 26.6 degrees, and the tangent of 26.6 degrees. And we're going to be looking for patterns today. So even though I emphasize that we want to write our answers in simplest radical form, for today, because we're looking for patterns, we're not going to do that. So as you do go through today's assignment, do not put it in simplest radical form. If you end up with a square root in the denominator, so be it. Just leave it there. We're going to look at some patterns. So I'm going to pause the video. You pause the video and see if you can answer these sine and cosine and tangent problems, and then we'll see if we get the same answer. So hopefully you did the problems. Now I'm going to do them. So sine of 63.4. So remember, the sine is the opposite over hypotenuse. That's the name of that relationship. So I can see from 63.4, the opposite side is 2, the hypotenuse is 5. So this is going to be 2 over the square root of 5. And I'm going to leave that square root of 5 in the denominator. The cosine is the adjacent over hypotenuse. I can see my adjacent side is 1. So this is going to be 1 over the square root of 5. And the tangent is opposite over adjacent. So the opposite side to 63.4 degree angle is 2. The adjacent side is 1. So this is going to be 2 over 1, or just 2. And then we're going to do the same thing for the other angle. So here I'm at the angle 26.6. So the sine opposite over hypotenuse is 1 over the square root of 5. So this is 1 over the square root of 5. The cosine is the adjacent over hypotenuse. So here is the adjacent over hypotenuse. So cosine is going to be 2 over the square root of 5. And the tangent is going to be opposite over adjacent, 1 over 2. So this is going to be 1 over 2. And then we're going to look at these and we're going to say, oh, do I see any patterns? So let's look at this. And here is the sine of 63.4 is 2 over the square root of 5. Well, here is 2 over the square root of 5. What do you notice? It's the other angle, the cosine of the other angle. And so the sine of one angle is the cosine of the other angle. And we've seen that before, and it's always true. So if I look at the sine of 26.6, it's going to be the same as the cosine of 63.4. And then the tangent, which has got that cool relationship of reciprocals. So if I take the tangent of 26.6, the reciprocal is going to be the tangent of 63.4. So they're related in that they're inverted fractions.